it's okay.
Because I have no feedback from.
No.
No, it's
No?
not full screen.
Click on the bottom on slideshow.
Yes, let's show. Close to the volume, bottom right. Oh, no, okay, that's
Okay, yeah, that should work. No, not yet.
Did it? It did not?
Not yet, but maybe we could proceed the two.
yeah. You can use.
Yeah,
the
you
same
can
way.
do this one.
You can do the. You can do this way. It's okay.
Okay. So sorry for these technical issues.
Yeah, better.
Okay, it's almost full screen now. My name is Georgi Fedorov. I come from the University of Eastern Finland. So I'm going to tell you about work that has been done previously during my stay at Moscow Institute of Physics and Technology and partly at Moscow State Pedagogical University. So here's my acknowledgement slide. Here is my acknowledgement slide with many thanks to different peoples and organizations with which we collaborate. So the outline of my talk is here. I will briefly tell how do we detect terahertz radiation, what are the main ideas, some preliminary results, and I will spend most of the time telling you a story about what I call plasmonic interferometry in graphene, which consists of two parts that I once again schematically call Fabry-Perot interferometer and towards Michelson-Morley interferometer, both for plasmons in graphene. Okay, so how do we detect terahertz radiation? So we have something which I don't show at the moment, embedded into a terahertz antenna. This antenna is on a silicon chip, on a small silicon chip, which is in turn located on a silicon lens to couple whatever you have inside the antenna to the terahertz radiation. So with this, you can work with very tiny objects. With such a setup, you can work with very tiny objects that have dimensions of less than 1 micron, but you still can probe their response to radiation to measure the photoresponse spectrum and do many other interesting things. But the first thing you do is you start with measuring the conductivity of the object you have. Just simply measuring applying some voltage, you measure the current, and you also have an opportunity to apply gate. In this case, you use the silicon wafer as a back gate electrode. Okay, so the response you can measure comes in two varieties. First, you can detect photoconductance. Like here I show two IV curves of whatever it is, and they have different slope. The IV curves measured with and without radiation. And this is what's called photoconductance. And the reason for that may be that you create electron hole pairs like in semiconductors, or you just heat this system, which is called bolometric effect, and so on and so forth. So there can also be another very different effect, which is that your IV curve doesn't really change the slope much, but what happens is that it shifts with respect to its original position, and there is a certain built-up voltage corresponding to zero current. So this is photovoltage. It's more or less something similar to what we get in the solar batteries, but on much smaller voltage scale. So this type of detection is in many cases preferential because you don't have to bias your device, you have smaller noise, and you have less power consumption to operate it. Where does it come from? It comes from different types of asymmetry that you built into your structure that you created. It may be parasitic asymmetry, or it may be intentional asymmetry. And this asymmetry will result in different effects. I illustrate here only photothermal effect, which is in building of a temperature gradient as response to the radiation. And this temperature gradient will result in photothermal power, thermoelectric power. So the red part here is supposed to be heated more because there, for example, there is worse contact properties on this side, right? So that's one of the effects that when asymmetry results in appearance of a photovoltage. You can also have a p-n junction inside the channel, so it will operate as a diode. Once again, this is what we have in solar batteries. And here are some examples of the structures we played with, asymmetric structures based on CVD produced materials, carbon nanotubes, like here, graphene, CVD grown graphene patterned into something, and graphene patterned into nanoribbons, and also individual nanotubes. And these are the hardest to work with because you always have to find them and then make the contacts. For these three, you just have a continuous layer of something, whether it's nanotube film or graphene, and you just pattern and put the contacts where you patterned your material. So these three are much easier to produce, but it turns out that individual nanotubes are the most responsive here. So the idea which we employed in these 4 structures is the same. We have asymmetric metallization, which is done in a single sputtering step. So you have thin vanadium, in this case, stripe touching your sample, your conductance channel, and you have a thin golden stripe touching your sample check conduction channel on the other side. And since these two metals have very different work functions, you create a p-n junction across the conducting channel, and that results in a large signal of photovoltage. Whether you call it large or not, it depends, but still there is notable photovoltage in response to terahertz radiation. So this is what we played with for some time, and we found again that individual nanotubes are the most responsive, but it's very difficult to reproducibly make such devices. And you get some interest in NEP, but the exact mechanism of this response is not properly understood, and it's different for individual nanotubes, graphene patterns, and graphene, which you can call continuous graphene. So I'm not talking about this too much. One important thing here is that we noticed some features of plasmonic response in case of CVD graphene and continued to go along this way. And this is the main part of my talk that is devoted to the results we obtained by concentrating on what happens with plasmons in graphene. So just as a brief introduction, what are plasmons? What is interference first? Interference is observed in many different situations. So optical interference is illustrated by this classical two-slit experiment where you have the same intensity distribution for whatever slit you open, but very different when you open both of them. And same thing happens if you let electrons, not light, electron waves go through the slits, and there's quite universal phenomenon. And the mathematical background of it is that you're in what you add to each other are amplitudes, and what you register is square of this amplitude, or actually any nonlinear function of the quantities that add up to each other. And it's very interesting and has many applications. So what do we know about plasmons in graphene, and can we play with them in the same fashion? So we know about plasmons, and I don't have time to prove it to you that in a gated graphene channel, plasmons are very simple. If you extend your velocity, for example, or non-local concentration of carriers as a plane wave, you get a very simple dispersion relation here, similar to that in acoustic waves. And the important feature is that you can tune the phase velocity of plasmons by just applying the gate voltage. That has already been mentioned by one of the speakers previously. And although this formula is obtained in a simple Drude approximation, for many cases, you can just replace the mass of the particle with the effective mass of the quasi-particles, and you can still use this expression and count on it to be true. Okay, and it's very promising because if you think about analogy with optics, you have a medium with tunable refractive index, and let's see if it helps somehow. So first of all, the simplest interferometer we can make is already there because we probe electrical properties of graphene. So we already have this source and drain contacts that we can think to operate as mirrors, although not very good, but still these are mirrors for plasmons. And we can obtain a standing wave here, and getting a standing wave may somehow change the properties of this device, and we have to find out how do we detect this situation. But still, the condition for a standing wave is written here. Importantly, it always has some correction to the numerator, which depends on the boundary conditions and the phase that a wave acquires when reflecting from the mirror. Okay, so we can think about using this graphene channel as or any other two-dimensional channel as a Fabry-Perot for plasmons. Now the question is, first, how do we excite the waves, and how do we what is the analog of the transmitted intensity? Because in regular optics there is light that comes from somewhere, and we detect it on the other side. And the question is, how do we make a plasmon come here, and what do we detect as a transmitted intensity? So the answer to these questions have been obtained long ago. First of all, you already have the gate, so you can couple it to terahertz radiation, and that will may excite the plasmonic waves inside the channel. And this situation was considered by Mikhail Diagonov and Michael Schur a pretty long time ago. And the answer to what happens here is that you will get rectification of terahertz radiation with this device. And this DC voltage will be depending on actually something like square of the current inside the channel. And if you can think about two plasmonic waves going, for example, from the other two sides of the channel, you would add up the currents, and you would detect a voltage that is proportional to the mean square of these currents. So it's pretty much the same thing as we have in optics. So we can observe some interference. Okay, so again, this interference influence on the frequency dependence of the response was predicted long time ago, but you need a very high mobility device for this. And another challenge is that you need to continuously tune the frequency in a wide range, and you want to avoid any parasitic interference in the setup, which is really difficult. So another approach is to fix the frequency and to tune the properties of the medium. That is to change the phase velocity of the plasmon by applying a gate voltage. And the realization of this, oh, sorry, I'm going other way around. So was suggested by our colleague Denis Bandurin back in 2017 or so. So the device is based on two-layer bilayer graphene, which is better in certain respect than single-layer graphene because its dispersion relation is not massless. So you have a finite effective mass that doesn't depend on gate voltage in a wide range. So you have better tunability. And encapsulated graphene is known to have very high mobility, so it can be used for this purpose. And then we use a standard antenna to couple the radiation between source and gate electrode, and we measure the voltage between gate and between source and drain. And as we scan the gate voltage first at a lower frequency of radiation, we see nothing special. But as we decrease the frequency of incident radiation, we see some oscillation type features evolving on. So what does it tell? It tells us that we did make a Fabry-Perot interferometer. We can approximate the response of this device with this ansatz, I would say, where R0 is this red line we obtained at low frequency. And this denominator describes what is known in optics, a very known textbook optics expression for calculating response transmission through the Fabry-Perot interferometer. So the RS and RD are reflection coefficients, which are small. They have to be about 1 for having a high Q interferometer, but in our case they are small. So the oscillations are not very high amplitude, but still it is they are there, and it is easy to understand why we don't see anything at low frequency, because these peculiar values of gate voltage, they scale as square of the frequency. So at low frequency we see nothing, at high frequency we see many modes. We are supposed to see many modes of resonance in this device, and the positions of these resonances are matching the theoretical predictions. And I don't have the slide illustrating that, but still I move on with this story, because what we have, it may be used for on-chip spectrometry to replace this Fourier transform, bulky Fourier transform infrared spectrometer, of which the principle is that you move a mirror, and in our case we tune the refractive index, effective refractive index of the medium between these mirrors. And in a Fourier transform device, we move the mirror and get this signal as a function of position of the mirror. And here we tune the phase velocity and get this signal as a function of gate voltage. Here you can do a simple Fourier transform. Here you cannot do a simple Fourier transform because the system is not very linear, but I believe that we can calibrate it in order to get a very compact on-chip spectrometer out of our good graphene. Now, another story begins with you can begin it with this consideration that actually Michelson-Morley interferometer is a bit better because you control the phase of the waves that reflect from the mirrors. And this is what we also did, but we did it in CVD graphene, so we don't see these nice resonances, but we see the effect of plasmonic interference. And I'm going to tell you, prove you that this was really the case. So this work was inspired by Valentin Kacherovsky from Yoffie Institute and Sergei Ganchev from Terahertz Center in Regensburg. And the idea is that we want to control the phase of plasmonic waves excited by different sides of the graphene channel. And in order to do this, we can do it easily. We do it in two steps. First, we bend the dipole antenna, make it less symmetric. And the second step is that we can start playing with the polarization of the radiation that falls on this antenna. And not to go too deep into geometrical issues here, to prove that the phase is tunable by rotating this λ/4 plate, we just consider two cases: circularly polarized radiation that goes this way, and you have phase difference of one side. You start rotating in another way, and you have phase difference between two signals here of the opposite side. When I say signals, I mean the potentials of the source and drain electrodes with respect to the top gate electrode, which I consider as the ground, the local ground of the experiment. So due to nonlinearities and due to this phase asymmetry that is embedded into the system, I may have this DC voltage signal that was calculated by Valentin and some time ago. And here I don't go into details, so it's quite a standard and rather easy procedure. And you end up with such an expression for the response, which is still pretty bulky to discuss in detail. So I just shrink it to these two terms. You have one term proportional to difference of the square values of potential on source and drain electrodes, and another term which is proportional to two amplitudes of these potentials, not these mean values, and sign of phase difference between them. So this term is important, and it results from this interference of plasmons in graphene channel. So in more general case, you have three terms: mean square of the potential difference, means difference of mean squares, and our nice term that describes the interference. How do we tell one from another? I don't discuss the origin for the time being. I just tell how do we tell one from another. We use this λ/4 plate, and we change the angle it makes with the polarization of the incident light. And we measure the dependence of the photoresponse as a function of this angle. And it's pretty easy to show that the first term here should be pi over 2 periodic function of phi, which is very straightforward and clear because you just come to the same polarization every 90 degrees. You have the same periodicity for the second term. Once again, you just come to a linear polarization state every 90 degrees. But for this term, every 90 degrees, you go to a circularly polarized light on the outcome of the lambda over 4 plate, but you change the direction of the electric vector rotation. So you go from sigma plus to sigma minus if you rotate the plate by 90 degrees. And this term is asymmetric. It has sign of this phase difference. So in general, this term will give you a pi periodic contribution to the response of the device. So this is our devices that we made and probed. They have gates that is not as wide as the channel itself, just not to screen the effect of the radiation at the contacts. It was not probably optimized structure, but still we see that aluminum oxide allows to shift the CNP point close to zero, which
You
is
have 5
also
minutes, Sergey.
good news. Yeah, I'm almost done. Yeah, thank you. So, and as for the response that we measure, just connecting the voltmeter to the source and drain electrodes, yeah, it turns out to be composed of two contributions. One is pi over 2 periodic, other is pi periodic, and you can actually remove each of them by changing the gate voltage or temperature. So here is a wider set of data illustrating what I've said. And the most impressive thing you can see, like here, for example, that for clockwise and anti-clockwise polarized circularly polarized light, you see the change of sign of your response. It's impossible to imagine for any of standard rectification mechanism. So it actually does signal us that responses to a significant extent is defined by the plasmons excited in the channel and interfering inside. So as a function of gate voltage, our effect is mostly pronounced at positive gate voltages, and it's the result of some parasitic asymmetry of the structure. So theory predicts pretty symmetric behavior. And what's more interesting, that this theory predicts that circular response should go to zero each time you have a standing wave inside the channel. So it will maybe a more handy way to probe these standing waves if we work with a higher mobility device, or maybe in different conditions. So we have to we can see it in CVD graphene by tailoring the channel length, frequency, and other parameters. Nevertheless, it is still to be done, seeing these zeros, which is of great importance. But otherwise, we demonstrated that the plasmon interference in the channel do contribute to the photo response. And by this, we prove that just graphene with two contacts may operate as a Michelson-Morley interferometer. And with this, I come to the main conclusions of my talk. So we demonstrated a Fabry-Perot interferometer and made with high mobility graphene, and it further can be exploited as a non-chip spectrometer for many different applications. And it also can be used to restore the single particle spectrum of the material that you work with. I didn't talk about this much, nevertheless, just believe me. And what is important, that we have clear evidence for plasmon interference at a distance of few microns and CVD graphene. I didn't mention it, but the classical decay lengths for plasmons within the Drudy theory that we used actually is about 100 nanometers. It's just the product of the plasmon velocity by momentum scattering time tau, and it gives you like 100 nanometers. But we see something on the much larger length scale, so we believe it may signify, demonstrate that plasmons close to Dirac points, close to the SINP, will be more survive through longer distances than predicted by classical theory. Okay, I think that I convinced you that plasmonics in graphene in the regime of is important when you do some photo detection experiments. And with this, I am happy to answer your questions.